Okay, I guess we're getting to a few people online. Good morning, guten Tag, goedemiddag. Hello everyone, welcome to the IGAC-iCACGP ECR conference for 2023, the first of its kind. My name is Max de Savetas and I'm joined by Emily Matthews. We are both postdocs and the co-chair of the newly established IGAC-iCACGP ECR Scientific Steering Committee. Thank you all for joining us. So for those who might not be aware, IGAC is the International Global Atmospheric Chemistry, and it is best known for the conference which takes place every 2 years and brings a lot of the atmospheric chemistry community together for this specific time zone. Last year it was in Manchester, and I think the last time it was in Europe before that was probably in Greece in 2010, if my memory is correct. IGAC stands below the International Commission on Atmospheric Chemistry and Global Pollution. So this is one of the commissions under the International Association Meteorology and Atmospheric Sciences, as you can see in this framework on your screen. IGAC was established in 1990, the Commission in 1957, and everything above that was established right after the Second World War in the 1940s. We are also alongside other societies such as SOLAS and ILIPS, which also relate and bring together scientists in relevant fields of science. The mission of IGAC is to facilitate atmospheric chemistry research towards a sustainable world, and this is done through having different activities that are relevant to specific research topics and working groups which are more focused on several regions, and you can find those highlighted in the GatherTown main hall. Going to the next slide, I think Emily takes over.
Yeah. And now, so presenting you this year's IGAC-iCACGP Early Career Science Scientific Steering Committee. So we formed at the start of this year, and for the past few months have been working hard to bring you this conference, which we really hope you'll enjoy and leave having made some new connections and talked about your science. So this is our first major event and part of our mission to reach, engage and support early career researchers in the atmospheric chemistry community. And so moving on to the events of today and a bit of housekeeping. All of today's sessions, except for the poster session, will be held in Zoom. The links can be found in the conference booklet, or you can enter via the appropriate room in GatherTown. For this morning's highlights talks, please use the Zoom Q&A function, which should be at the bottom of your screens, and we will then try and get through as many as we can. For the Icebreaker Climate Activity and Skills Workshop, we really encourage you to have your video microphone on for these, as these will be interactive. The in-person IGAC conferences have always put on a great series of ECR events outside of the scientific programme to facilitate networking. So we hope that these sessions will replicate to some extent, and that by meeting some new people, you really will be able to get the most out of these poster session at the end of the day. So I really encourage you to attend all the sessions that we've put on today. And remember to be your poster for your 20-minute window if you're expecting to be considered for one of the poster prizes.
Some further housekeeping, which I forgot to do in the introduction slide. For those of you who are not as comfortable with English, maybe, you have the options to put subtitles and have the language translated to your language. So I will say that in French as well. Pour ceux d'entre vous qui ne sont pas aussi confortables avec l'anglais, vous avez l'option de mettre des sous-titres et de l'avoir traduit dans votre langue, y compris le français. So the GatherTown that you've hopefully entered the conference through has the main hall with all the different IGAC activities and working groups, which I was mentioning before. Informations about IGAC and the conference next year in Kuala Lumpur, Malaysia, and the sister organizations to the lower left and our sponsors to the lower right. To interact with any of the objects in the room or throughout the rooms, you have to just press the X key on your keyboard. This is also true once you're inside the poster room to have a look at the posters or the whiteboards. And as we mentioned, the talks are through the plenary or the side meeting room as right now. The next slide. So we also need to say a big thank you to our sponsors. So this event is funded by the European Space Agency, Future Earth, the National Centre for Atmospheric Science in the UK, the International Atmospheric and Meteorology Association, and the Copernicus Publication Group. And they are funding all the licenses that we're using, obviously, but also the 6 poster prizes, which will send 6 of you to Malaysia for the IGAC conference next year. We also owe a big thank you to the IGAC-iCACGP and the IGAC steering committees for the support, and particularly the director of IGAC, Dr. Langley-Dewitt, who has done a lot of the administration with us. Without further ado, I will give the floor to, I think, Martin, who will introduce our speakers for this session. Thank you.
Yes, thank you, Max. Also, warm welcome from my side. And I'm very happy to announce our first speaker for today. That's Dr. Nancy Fakhri. She's a lecturer and research affiliate at the St. Joseph University in Lebanon and at the Climate and Atmosphere Research Center of the Cyprus Institute. She will have a talk on chemical characterization and contribution to ambient concentrations in the East Mediterranean Middle East city Beirut. So Nancy, the floor is yours. We can see your slides.
Hello, everyone. Just one moment. Can you see my slide?
Yes. Can you do it in presentation mode?
Perfect.
Okay, great.
So hello, everyone. Thank you for the introduction. So in this presentation, I will be discussing the PM sources in the East Mediterranean, Middle Eastern city Beirut, chemical characterization and contribution to ambient concentration. So air pollutant can originate either from natural sources, such as sea salt and volcanic emission, or from anthropogenic sources, such as transportation and industrial emission. These sources will emit gases and particulate matter. Particulate matter is generally classified based on the size distribution. We define, for example, PM2.5 as particle with a diameter less than 2.5 micron. So this particle can enter the human respiratory tract. Small particle can penetrate deeply in the respiratory tract, reaching the alveoli and bloodstream. The exposure to PM leads to various health outcomes, for example, cardiovascular and respiratory diseases, heart diseases, and lung cancer. The health effect depends on the exposure effect function, which is very variable across the crowd. As presented in this figure, some populations are exposed to low PM concentration, for example, the countries represented in green color, while others are exposed to higher PM concentration, which are represented in red color, for example, the Middle East. Lebanon represents one case study of this region. So Lebanon is a Middle Eastern country with a population of more than 6 million people. Beirut is the capital of Lebanon. Greater Beirut area is a typical agglomeration in the East Mediterranean Middle Eastern region with a population of around 2 million people. Previous studies conducted in Lebanon have reported that the average PM2.5 concentration were 6 to 10 times higher than the WHO guideline of 5 microgram per cubic meter. The high PM concentration can originate either from local and long-range transport sources and from natural and anthropogenic origin. The trend in emission was increasing if greenhouse gases were taken as a proxy. Moreover, on top of the trend, there have been some displacement from Syria to Lebanon due to the war, which also resulted in an increase of up to 20% in emission of air pollutant in Lebanon. Our research group at USG is currently preparing an updated version of the emission inventory between 2010 and 2014. And if you look at this figure, in 2014, 35% of PM emission originated from private diesel generator. So because the National Electricity Company does not provide electricity 24 hours per 7 days, the Lebanese citizen use private diesel generator during the power cut. Air quality in Lebanon is also affected by road transport, which were responsible for about 20% of PM emission. So since Lebanon does not have an effective public transport system that covers the entire country, the Lebanese citizen mainly relies on private car and account for about 80% of the Lebanese fleet. 15% of PM emission were attributed to open burning of waste. Lebanon has always suffered from waste problem, and the big crash was in 2015. The Ministry of Environment in Lebanon have started in 2013 the installation of an air quality monitoring station. A total of 17 stations were installed over different phases. The Air Quality Protection Law was published in 2018, stating that the air quality standard should be at least as stringent as WHO guideline. However, no ministerial decision have been issued yet to update the national standard. So if we consider that the current WHO guideline ensure the least impact possible on health, and if policymakers would like to reduce the PM emissions to meet the WHO recommended values, they should fully characterize the PM. Since this characterization was not achieved earlier, then it is of utmost importance to answer our scientific question by determining the chemical composition of PM 2.5 in Lebanon and determining the sources and their contribution, whether natural or anthropogenic. So to address our scientific question, the following methodology was adopted. First, aerosol sampling was conducted. After that, a detailed chemical characterization of PM was performed. Then, positive matrix factorization was used to identify the sources and their contribution. So, aerosol sampling was conducted at 3 sites in Lebanon. A total of between 70 to 100 samples per site were collected using a high volume sampler. Chemical analysis was performed on subfraction of the filters. Organic tracers were analyzed by GCMS. Major and trace elements were analyzed by ICP-MS. Soluble anion and cation were analyzed by ionochromatography, and elemental and organic carbon were analyzed using the thermo-optical transmission method on a Sunset laboratory analyzer. So now moving on to the results. The average PM 2.5 concentration found at the 3 sites were approximately 30 microgram per cubic meter, which is 3 to 6 times higher than the WHO guideline, depending on whether we consider the old WHO standard during the sampling period or the new applicable WHO guideline. Trace elements such as cadmium, cobalt, nickel, for example, are toxic to human health even with low concentration. So in this study, we have used the concentration of these elements and the health risk assessment model following the US EPA model to determine the health risk associated with the exposure to these elements. So according to the US EPA, a cancer risk value of 10-6 indicates 1 additional case per 1 million of people. So, as presented in this figure, the sum of the risk posed by the exposure to the metals indicated 33 to 45 additional cases per 1 million of people. Now moving on to the PM2.5 sources. In Beirut, 11 sources were identified. At USG and Mkayel, one additional source was identified on top of those identified in the Beirut site, which is the cooking emission based on the contribution of fatty acid. The crustal dust factor was identified by high loading of calcium, iron, titanium, and aluminum. The time series of this factor peaked between the 3rd and 6th of May, which may indicate a dust storm. We have also calculated the elemental ratio, and they were in the range of African dust. To further confirm the origin of the dust storm, the backward trajectories using FlexPart model was applied. The red color showed the region where the emissions are most important. Backward trajectories, using FlexPart indicated that this event originated from North Africa. The secondary inorganic aerosol was identified by high loading of ammonium and sulfate. Sulfate concentration in Beirut are generally low, and sulfate is generally from long-range transport. PSCF analysis show that this source originated from sources in Turkey and the Mediterranean Sea. The oil combustion factor was identified by high loading of vanadium and nickel. Previous studies conducted have reported that Turkey and Eastern Europe are the dominant origin. FlexPart Retropume have showed that the TEE cluster has presented the highest number of samples, indicating that Turkey and Eastern Europe are the dominant origin of air masses during our sampling period. So, we can conclude that these three sources have originated from long-range transport. Crustal dust, which was a natural source, and the secondary inorganic aerosol and oil combustion, which are anthropogenic sources. So if you want to summarize the sources in Lebanon, first, our work has pointed that Lebanon's geographical location, such as its proximity to the Mediterranean Sea and the African dust storm, are an important contributor to the high PM sources from natural sources, which cannot be mitigated, making the WHO guideline of 5 micrograms per cubic meter unreachable. This is also the case in other Middle Eastern cities such as Riyadh, Makkah, Cairo, for example, where desert dust has a high contribution to PM and sometimes dominates the PM mass concentration. Second, we have also identified that anthropogenic sources such as oil combustion and the secondary inorganic aerosol also originated from long-range transport, so they cannot be controlled locally, but only through international agreement. So this leaves us with 51% of local controllable anthropogenic sources, which accounted altogether to approximately 16 micrograms per cubic meter. So to effectively reduce the PM, this work has identified several local controllable sources, for example, road transport, diesel generator, and biomass burning. So following the same strategy in Beirut, so natural sources accounted for approximately 9 micrograms per cubic meter, which is almost 2 times higher than the WHO guideline. Sources originating from long-range transport, which are not controllable locally, accounted for approximately 7 micrograms per cubic meter, which almost leaves half of the contribution to the local controllable sources, which accounted for approximately 13 micrograms per cubic meter. At Zouk site, natural sources accounted for 16 micrograms per cubic meter, while the anthropogenic and controllable sources accounted for 6 micrograms per cubic meter, which leaves 11 micrograms per cubic meter to local controllable anthropogenic sources. So the WHO recommended values are not achievable in the Middle East. And if we only consider natural sources, but are they applicable as a legal air quality standard to the Middle East region? So our research group went a step ahead and attempted to assess the health impact of PM using the oxidative potential measurement. So the oxidative potential approach focuses on the capacity of PM to generate reactive oxygen species that will oxidize biological molecules in tissues or in cells in the lungs. So in this study, we have done the evaluation of the oxidative potential based on two methods that are commonly used in the literature. So the ascorbic acid assay and the ditreitol assay. So not all sources that we have identified will have the same priority for, after considering the oxidative potential. So if we look at this figure, crustal dust, which presented a high contribution to PM, was found to have a limited impact on oxidative potential, while some local sources that are locally uncontrollable, for example, the marine one or the biogenic PM, may have also not seen to have an impact on health. However, when we consider the several local controllable sources such as biomass burning, the diesel generator, they have showed high oxidative potential. So the emission inventory and also the source apportionment results that we have done have showed that both road transport is an important source of pollution. Therefore, it should be investigated in a deeper way. So a tunnel study was conducted in Salim Islam for 5 days, where we have collected simultaneously filters inside and outside the tunnel over 14 sampling periods. After that, chemical analysis was performed on subfraction of the filters, and the emission factor, which is defined as the mass of pollutant per unit of fuel consumed or distance driven, was calculated for the Lebanese fleet. So the emission factor of PM2.5 component, including OC, EC, ions, elements, and organic compounds, were calculated and compared to results of other tunnel studies. HGVs were not allowed to circulate on weekends and in the morning and evening on weekdays, which allowed us to isolate the LDV from the total fleet. So when we look at our results, we have found that the emission factor were 2 to 5 times higher in Salim Islam compared to other tunnel studies. The high emission factor could be explained by the high vehicle age in the Lebanese fleet, the local maintenance practice, for example, the removal of catalysts due to its high maintenance cost, along with low weak enforcement. Finally, to assess the contribution of exhaust and non-exhaust emission in Beirut, we have explored the sensitivity of the chemical mass balance to source a profile of exhaust and non-exhaust emission obtained through positive matrix factorization from 3 sites in Lebanon, the sites that I have presented, Zoo, Beirut, and USG. CMB results have revealed a high contribution from non-exhaust emission. So non-exhaust emission are caused by the resuspension of road dust, abrasion of brake and tires, and deterioration of road surface. So in conclusion, in the study, a detailed chemical characterization was performed and a detailed source apportionment was achieved in Lebanon. And based on our results, we have found that natural sources of PM does not allow us to achieve the WHO recommendation in Lebanon and the Middle East. Preliminary results have showed that natural sources does not derive the oxidative potential values, which means that it's not always beneficial to mitigate the major sources of PM to enhance the health of population. At the end, my research group and I would like to acknowledge all the funding we have received. Thank you for your attention.
Thank you for a great talk, Nancy. And thanks to the people who've already asked questions. If you have any questions, please put them in the Q&A and then I will read them up and hopefully Nancy can answer the questions. The first question is from Liselotte Tinel. She's asking whether you've considered marine traffic as a source for the vanadium nickel factor, because marine fuel can be a source of these metals too.
Exactly, but we have done a FlexPart retrodiplome, and we have found that 88% originated from long-range transport when based on the FlexPart.
Okay. Luna Carteret is asking whether the WHO recommendation takes into account the quite strong influence of natural sources that you showed us in this presentation.
WHO has only PM only takes into account the mass concentration, so which is 5 microgram per cubic meter. So it does not matter if it comes from natural or anthropogenic sources. But the Middle East is highly affected from natural sources, which is usually from crustal dust originating from desert dust.
Okay. The next question is from Varun Kumar, who's saying he assumes you did the OP analysis on total PM. How did you apportion OP contribution to individual sources? Was it through multilinear regression?
Exactly. So if I show in this slide, we have used a multiple linear regression to associate them together.
Okay, and then he has a second question on SIA sources.
Mm-hmm.
You said it had sources in Turkey and in the ocean. Does this mean shipping emissions of SO2?
Yeah, so we have done for the secondary inorganic aerosol, because this part of the was done in summer. So usually we have it's coming because Turkey, and then we have the Mediterranean Sea and Lebanon. So it's coming through the above the Mediterranean Sea and arrives to Lebanon.
Okay. And a question from Ben Triff, who's asking the marine contribution to PM 2.5 is slightly higher, and if water levels might be the cause of PM 2.5 concentration exceeding the WHO guidelines.
So it's not the marine one, it's the natural sources, it's higher. So the combination of the natural sources, which is crustal dust, marine, and biogenic PM, are all together are higher than WHO, and not only the marine. So if I combine these 3 sources from natural sources, all these together are higher than the WHO guideline of 5 microgram per cubic meter.
Okay. We have time for a couple more questions if anyone has any questions. There's no more left in the Q&A. No? Then, oh, there's a question from Damaris Tan. What is the main component of the natural marine sector? Is it mainly sea salt?
Yes. Sea salt, sodium, and chloride.
There are no more questions. Then I think we move on to our next speaker.
Thank you so much.
And let Stephen present our next speaker.
Okay, yeah, thanks, Simone. Yeah. So hi, everyone. Yeah, so we're going to move on to our second highlight speaker of this plenary talk session. So this is going to be given by Samuel Cliff, and he's a final year PhD student in the Wolfson Atmospheric Chemistry Labs at the University of York in the UK. And he's going to give a talk on the unreported VOC emissions from road transport, including from electric vehicles. So Sam, if you want to share your slides, and the floor is yours.
Okay. Is that all right?
There we go. Yeah, it looks all right, Sam. Yeah, so fine. Yep.
Lovely. Yeah, thanks for the introduction and the invitation to discuss some of my research here today. That was a great talk by Nancy, so that's going to be a tough act to follow, but I'll try my best. I'm I'm going to be talking today about a case study that we did a couple of years ago now, that focuses on air quality, and in particular, volatile organic compound emissions from road transport. And although I'm presenting today, I just wanted to highlight the numerous other people who have contributed to this work and that I've listed on screen. So a big thanks to them. And to set the scene a little bit, I'm going to go with the assumption that everyone is aware that air pollution is bad and there's a significant societal benefit to improving air quality. And in terms of the adverse health and environmental effects, what we're most interested in is air pollution concentrations. And the WHO publishes guidelines for concentration limits for each of the criteria air pollutants. But concentrations can be quite tricky to interpret because they're influenced not only by emissions, but also by factors such as meteorology, chemistry, and atmospheric deposition. The only thing that we can actually control are the emissions. And so when we introduce air pollution abatement strategies, what we're trying to do is reduce concentrations via the reduction of emissions. And that's why, in addition to concentration limits, we also have things like emission ceiling legislation, which limits emissions of different pollutants. And then another important part of the kind of air quality feedback loop is an emissions inventory. And this is where we collate the location and magnitude of all the different emission sources. Okay, and an example here would be the NAEI for the UK. And these emissions inventories are what are used to identify which sources to target in policy decision making. Unfortunately, these decisions will only ever be as effective as the accuracy of the data informing them. But what this means is that there's a real value to being able to directly measure an emission or an emission factor, because you can verify the accuracy of the inventories, and you're actually measuring the variable that we are trying to control. And I'm sure you're all aware that VOC stands for volatile organic compound, and it represents a whole class of compounds that includes things like benzene, ethanol, and acetone, to give a few examples. And whilst they're not one of the criteria air pollutants, they play a very important role in the secondary formation of ozone and particulate matter. And so they're still often included in emissions ceiling legislation, and we track them in our emissions inventories. And so the plot on screen now is UK estimated VOC emissions from our National Atmospheric Emissions Inventory, and that's for the last few decades. And you can see that there's been this significant decline in recent years, and that's because of the success of policies that control emissions from fossil fuel sources. And what we found is that as the fossil fuel sources have been controlled, that they've been replaced by solvent emissions as the dominant source. So that's the light blue boxes in the figure. Historically, though, of course, all of the air quality research has been focused on those fossil fuel applications because they were the most important at the time. And what this means is that as a direct consequence of being minor in the past, these sources of emerging importance, they typically have a larger uncertainty. And that is where we come in with our measurements to try and reduce this uncertainty. And this presentation is going to focus on some work that we did on evolving sources in the road transport sector. And you may have seen on the previous slide that the road transport sector has consistently been a key source of air pollutant emissions, and that is primarily out of the exhaust. And then for VOC specifically, we get fuel evaporation from the fuel tank as well. But the reason we've seen this rapid decline is because of the widespread implementation of technologies like the catalytic converter, which controls exhaust emissions. And then we also have carbon canisters now, which control evaporative emissions. And as we electrify the fleet and remove the fossil fuels, it might be intuitive to think that the emissions will decline towards zero. And this is widely assumed from a VOC perspective. At least in the particle space, there's this growing pool of research on non-exhaust particulate matter from things like brake and tire wear. And you saw the significance of this source in the last talk. And that is because these will still be present despite fleet electrification. But what about non-fuel related VOCs from car care products such as screen wash? Right, that hasn't really been thought about before. And so we decided to investigate. And to do this, we used what's known as a roadside increment methodology, which facilitates the calculation of fleet average emission factors for different VOCs. And the way that it works is by using the difference in concentration between a roadside and an urban background site, or the roadside increment, and it converts it into an emission factor using a correction based on a tracer species, which has well-known emission factors. So if we take carbon dioxide as an example tracer species, we know the speed-dependent emissions of CO2 from each vehicle type pretty well. And so what we can do is monitor which vehicles pass the roadside site and their speed. We can estimate their emissions from a database. In this case, it's the UK's government's emission factor toolkit. And then we can link these emissions to the roadside increment concentration via this dilution factor. And once we've done this for a tracer species, we can use the dilution factor to estimate emissions for our VOC species and their own roadside increment. And these are the sites that we chose for the measurements, which are in Manchester in the UK. And the reason for this was to kind of take advantage of a big collaborative campaign that had the Manchester Air Quality Super Site fully kitted out with almost every piece of atmospheric instrumentation that you can imagine. And this acted as our urban background site, and it's pictured in the bottom left of the screen on a sunny day for once, which may come as a surprise for those who visited IGAC last year. And then for the roadside site, we took our mobile laboratory, which is the van in the top picture, and we took this to a busy dual carriageway just outside of central Manchester. And this site we chose because it was next to a fancy traffic camera that gave you a full fleet breakdown. And I have to say, this wasn't my favorite place in the world to do field work, mainly because it was on the same street as the Manchester Royal Infirmary. And I think the 5 or 6 ambulances which went past every hour would be enough to send even the best of us a little crazy. But we did manage to do 2 3-week measurement periods, one in the summer of 2021 and then one in the winter of early 2022, where we sampled about 1 million vehicles in total, so a healthy sample size. And then this is our mobile lab, which really facilitated the measurements, because we're able to park this up wherever is required, as long as we can get a power source. And we have all sorts of kit in here, but most notable for those that are interested is our selective ion flow tube mass spectrometer for rapid measurements of VOCs, which, if you're not familiar, is very similar to a PTR. And then we also have our cavity-based UGGA for measuring carbon dioxide. And of course, we carried out all of the good stuff like regular multi-point calibrations and zeros using the in-house built calibration deck. But in the essence of time, if you would like to know more about the van, I will direct you to this paper at the bottom of the screen. Okay, so we've measured some emission factors, which I will show you on the next slide. But to understand their significance and to put them into context, we need to compare them to what the emissions inventories think they are. And for that, we're going to use some software called COPERT, which is kind of the internationally applied methodology for estimating emissions from road transport. Okay, so all of the emissions inventories use this. And it's effectively a database of many equations which estimate emissions based on a number of input variables. So we input the traffic flow breakdown at the site, the different meteorological conditions, because emissions are quite dependent on factors such as temperature and relative humidity, and then also various other UK specific characteristics. And essentially what we end up with at the end is an emission factor in a milligram per vehicle per kilometer format that we can directly compare our emissions to. So moving on to the data, what I've got plotted here are the measured emission factors for a few species, and they're the red and yellow box plots, depending on what tracer species we used. And then we have the inventory estimated emissions for exhaust and evaporative sources in blue and green bar charts. And what we found is that for the aromatic species, which I've enhanced in the top right, we get a pretty good agreement between measured and inventory estimated emissions. We do have some small discrepancies, but we kind of expected this because the fuel blends are continuously changing and the VOC profile will change as a result. The agreement is probably not surprising because these are good fossil fuel tracers, which have seen significant regulatory attention in the past. Whereas for the alcohols, ethanol and methanol, we've got this massive underestimation. And it's clearly a source that the inventory is not picking up on. And what we found is that the discrepancy between measured and inventory estimated emissions for the alcohols, it actually agrees remarkably well with scaled industry sales statistics of screen wash. So that's 64 versus 58 milligrams per vehicle per kilometer. And that is actually a source that is larger than all other vehicular VOC emissions combined. And it's missing from these road transport emissions inventories. We were actually so surprised by these results that we even did some laboratory headspace analysis of different UK screen wash blends. And this confirmed the ethanol to methanol speciation that we measured in the field. So we're pretty sure that this is what it is. But what do these findings kind of mean as we look into the future? Well, if I direct you to the top left of this figure, you can see future projections of UK VOC emissions from road transport. Where in yellow, what we've got is the fuel-related emissions, or your like traditional VOC emissions. And then in red, we have the non-fuel emissions from screen wash. And in contrast to those predictions, which assume that the emissions will decline towards zero, or as is simply shown in that trend of the yellow bars, what we actually see is a minimal change in emissions over the coming decades, which may actually start to increase after 2045. And that's because the screen wash emissions will still be present despite fleet electrification, and they will actually increase with a predicted increase in vehicle kilometers traveled. And that's because of things like an increased population, and then the fact that electric vehicles are cheaper to run, so people tend to drive them further. And although I've kind of presented the UK figures here, I put this map at the bottom, which shows all of the current pledges to ban new sales of petrol and diesel vehicles around the world. And that was just to really highlight that this could be a transition of global interest. And then moving on to the kind of policy angle, what's perhaps most interesting is the sheer size of the screen wash source. It's about 6% of total UK VOC emissions, which is pretty significant. And if you think back to the start, when I mentioned emission ceiling legislation, the UK still requires some emissions reduction to meet the 2030 target. And I've tried to show that in the figure there with the black lines. And so this makes the screen wash source quite an interesting area for intervention, because by VOC standards, it's a pretty simple source, and it may just require some simple reformulation to reduce emissions. So that could be the replacement of ethanol and methanol, which are in there for their antifreeze properties. If you replace those with compounds that are less volatile, that might help. And I mentioned that the source is not included in road transport emissions inventories, and that is an important detail. For the UK, it's not really an issue from a total emissions perspective, because we put a lot of time and money into producing a very detailed emissions inventory. And so for us, the source is included as a solvent emission. But there's a clear benefit to being able to have the emission associated with the right sector, okay? Particularly because the road transport sector is unique in that the activity is generally well known in both magnitude and location all around the world. And that makes the emissions estimations accessible to all those other countries who are unable to compile detailed solvent use data. And even for those that can, like us, changing the emissions to the road transport sector will lead to a much better spatial disaggregation for improvements in air quality modeling, especially when you consider the chemistry implications of the co-emission of NOx from road transport, which is uncommon for a lot of VOC sources. And so what we will find is that models which do not include these non-fuel related VOCs will actually underestimate ozone production due to the sheer size of the VOC source. And there may be some interesting implications for things like PAN production, because we have this massive emission of ethanol in the presence of NOx, as well as high production rates of the smaller toxic aldehyde compounds as well. But we haven't really looked into this from a modeling side yet. And that's all I have. So thanks very much for listening. And I'm of course happy to take any questions.
Thanks for a great talk, Sam. Perfect timing. We have a couple of questions already, but if anybody else have questions, please just put them in the Q&A. The first question is from Wabena, who's thinks it's a very interesting study. Can you give him an idea of the estimated cost of undertaking this study?
That is a tricky question to answer. I would say from scratch, very, very expensive, because we had to build the van and fill it with the kit. So just the mass spectrometers alone are a few £100,000. And of course, you have to have two of them because you have one at the background site and one at the roadside site. But that's, I mean, but because we already had all this equipment, for us, it basically cost nothing. And that's why we chose to do it at the time we did, because we didn't have to worry about the background site. Those measurements were already being made. All we had to do is park the van up, and the cost of electricity was the cost basically, and my time, but that's not worth much.
Okay. Next question is from Eva Vanestil. Does your inventory include cooking VOC emissions? Some studies suggest cooking is a big source of ethanol. How do you estimate cooking versus screen wash as an ethanol source?
So we don't need to include, for this particular study, any of the emissions outside of road transport. And that's because we're looking at the roadside increment specifically. And so those emissions are only coming from the road transport sector. Yeah.
Okay. Next question. Again, thank you for the great talk. Is there a contribution of ethanol composed fuel evaporation or combustion in the concentrations that are measured?
Yes. So we do have the inventories do have an ethanol emission, because in the UK we have 10% ethanol by fuel now in our petrol, and so this is included. It's just tiny compared to the emissions from screen wash, and you can see it as the little bar at the bottom there. Yeah.
Okay. Question from Luna. Very interesting and well done presentation. Do you have any idea which model you will use to model this in the future?
I am very much not a modeler, and so I am probably not the best person to answer that. I was hoping that by presenting that someone else might like to think about investigating these things rather than myself.
So it sounds like if there's any modelers out there that want to do it, just contact Sam. Then a follow-up question to the cost question. How do you think such a study could be replicated in sub-Saharan African cities?
I would say, again, that it would be quite tricky if you don't have the infrastructure with a significant amount of background monitoring sites already. I would also maybe suggest that in some of the African cities, you will still have pretty high VOC emissions from fuel. The only reason they're so low in the UK is because of our modern vehicle fleet. And so the emissions are really restricted, whereas some of the older vehicles still have significant emissions from the fuel. So it might not be as big of an issue compared to the actual fuel emissions in some of the African cities.
Okay, I think Emily has a question.
Thank you. Great talk, Sam. I was just wondering if you've had any interaction with like policy or industry about all of this research and what their response has been.
We haven't had any interaction so far. It only has come out very recently as a published manuscript. So yeah, we will see if anything happens from it in the future. Yeah.
Thank you.
A question from Khan for modelers. Will a gridded emissions data be made publicly available for modelers?
So for the UK, they have gridded VOC emissions, and you could probably tweak those emissions so that the screen wash emissions were associated with the right sector, but having it as a per vehicle kilometer metric means that if you have your road transport emissions gridded, then you can just apply that factor as well.
Okay, and Stephen is asking, do you think this increase in VOCs will have a significant impact on surface level ozone concentrations?
So it will likely have an impact. I am not sure it would necessarily be that big of one, purely because ethanol and methanol aren't actually that ozone forming. If I go to this plot here in the top left, although we're expecting this, it's a small decrease over the next 3 decades. All of this yellow stuff is going to be a lot more ozone forming, and so we will probably see a decrease still, even though these ones are increasing.
Okay, I think we have time for one last question. Lieselot is saying, thanks for a great talk, very surprising results. These are very intermittent emissions, however. How have you estimated the duration of these emissions? Or would evaporation while not actively using the screen wash be important too?
So they are obviously very intermittent, which is why we measured for the 6-week period, and it's just kind of luck whether or not you get someone applying screen wash. But the hope was that measuring it over such a long period and that many vehicles that we would capture a good amount. Regarding evaporation, I don't necessarily think that evaporation while not using it is much of an issue because it's in a stored bottle. It's mainly the spraying and then that just over such a large surface area and then evaporating straight off that, which is most of the emission.
Okay, I think that's gonna be the last question for now. There's one question left, Sam, but you can type in an answer afterwards if that's possible. Thank you for some great answers. I will send it over to Martin to introduce our next speaker.
All right. Thanks also from my side, Sam. Very nice talk. And now we will have as a final speaker in this morning's session, Priscilla Adon. She's a PhD student at the University College of Dublin and a research associate fellow at the RQO project Afritech. And she will give and talk on AI-enabled air quality monitoring and management. So thank you, Priscilla. Nice to have you here. Please share your slides and you're ready to go.
Thank you, Martin. Can you see my screen?
Yes.
Okay, I'll just go to slideshow.
Perfect.
Oh, yeah. I think I need to minimize this. All right, thank you for the introduction, Martin, and hello, everyone. So for today, I'm mostly going to highlight some of the applications of artificial intelligence in air quality monitoring and management, and most especially focusing on the use cases at AirCo, some of the tools we've developed at AirCo using artificial intelligence. Maybe for those who don't know AirCo, we monitor air quality on the African continent using low-cost air quality sensors. So maybe I believe most of the participants here are very familiar with maybe atmospheric science or air quality in general. So I'll just rush through the introduction. Hopefully everyone is sort of up to speed. So I think one of the main challenges we have in sub-Saharan Africa is we do have high levels of air quality from the preliminary analysis that has been done, but the data, we are still like lagging behind when it comes to air quality data because of the high, like the cost of traditional monitoring is not it's very high, and most low and middle income countries cannot afford to have the high spatial resolution of air quality data using the traditional reference grade monitors. So that is why EACO was formed, and we use low-cost air quality monitors to fill the data gaps. As you can see from the map, if you compare Africa, much as we've already tried to really install over 270 monitors, you can see that the continent is there are still so many gaps, air quality data gaps that we still need to fill. And so that is where AI comes in. We are currently using AI to fill in some of the gaps where we do not have the low-cost monitors, but also use AI to generate additional tools that give insights into how air quality varies, or air quality forecasting, calibration. And these are some of the use cases that I will be talking about in a little more detail in the next slide. As I mentioned, we use low-cost monitors, and our monitors are locally developed at EACO. And why we decided to develop them locally is because we wanted to be able to customize these monitors for our environment or for our settings. And to do that, and some of the things we've done to customize these is to make sure they have like flexible power and data access configurations. For instance, we are able to use both solar and electricity, because there are some places we are interested in monitoring, but we do not have electricity there. So our devices can use solar. And then we can use both Wi-Fi and GSM, because Wi-Fi is not widely spread as in some of the developed countries. So we do leverage the GSM network, which is more widely spread in low income settings. And once the monitors are deployed, we send the data to a custom-made data management platform that was also developed by the EACO team. And on this platform, we are able to now work with data, and most of the tools that I will be sharing are the data, and the tools are hosted on this platform. We have so far deployed over 270 low-cost monitors across Africa. And of course, each bubble represents a location, but most of them are concentrated around East Africa, where we started our works. And we are now currently expanding into other parts of the continent, including South and West Africa. So the first application I will talk about today is sensor placement optimization. So the general rule is every location is a potential candidate for air quality monitoring, but you do not have monitors to put in each and every location you would like to monitor. So how do we now decide which place we place the few monitors that we have? So much as we are using low-cost monitors, we cannot still afford to put them everywhere. So we decided to build a tool, because the idea is to be able to get to have a monitor at least in the different locations with the various profiles. So if you have a location that maybe two locations that have the similar pollution profiles, then you don't necessarily need to put in both. You can put in one and then learn how air quality varies, or maybe use some of the insights you've gained in location A, and whichever metrics or you come up with to manage air pollution in location A can be applied to location B that has the similar profile with A. So we decided to use a tool, since our monitoring area is quite large, sub-Saharan Africa. So you have a tool that is powered by machine learning. You choose the geographical area that you're interested in, and you specify the number of devices that you have for that given geographical area. The tool is then able to make recommendations of the locations where you can deploy your monitors, and then the recommendations made by the tool are of course evaluated by domain experts to make sure it's actually feasible to deploy a monitor there. Or if it's not, then you can always find a location that is nearest to the recommended location. To build a tool, we use the geocensus data from the Uganda Bureau of Statistics. And some of the features we included in the machine learning module include the population density. Of course, these are some of the factors that would affect air pollution in a location. So like population density, distance from major road, the type of fuel that is used in the area, is it a commercial area, is it a residential area, and things like that. So we included quite a number of features. And then we use the elbow method to form the clusters with similar profiles, and then k-means clustering to then choose the exact parish where the sensor would be placed. And this is an example of what the interface of the tool looks like. So if I'm to specify that I have five monitors for this given polygon that I have selected over the city of Kampala, when I run this, it will now, so the bubbles are basically the recommendations that the tool has given. And of course, it narrows it down to latitude and longitude. So the experts, our hardware team, who can now go to these specific locations and sort of analyze the site and see whether it's a good place. It could be, say, in the middle of the road, so you could find a location that is near that place. So we found the tool to be very useful, especially when you're working with a large area and you cannot move around everywhere. So at least it gives you a starting point. The second, and actually these are two use cases, air quality predictions and forecast using AI. So as you can see, this is basically from the previous tool. We've now, say, placed monitors in the locations that were recommended, but there's still some locations that aren't necessarily covered. So how do we get a picture of what air quality is like in that location? So we also use artificial intelligence to estimate the air quality in the locations that do not have monitors. And we have used the Gaussian process regression model to build the air quality prediction tool. And for the model, we use PM from the known, so you use PM from the locations around your area of interest, and then latitude and longitude plus features from timestamp to estimate pollution in the location where you do not have the monitors. And so this is what the output of the tool looks like. So say it will not give you, like, say, this latitude and longitude, this is the air quality, but it gives you sort of a heat map to give you like a general overview of what air quality in that area looks like. And it is a great, this is more useful when we are doing, say, macro analysis. Say you're comparing one region or city by city. So it may, instead of looking at points, you then look at, say, the general air quality of the region compared, maybe say from city A and city B. And it's great for, especially when you're looking at working with policymakers and people who make decisions. They are not usually very interested in the points values. Yeah. Then also, we also do air quality forecasting using artificial intelligence. And this is basically predicting air quality in the next, excuse me, in the next 24, okay, in future. So for us, we do, could you give me a minute? I think I need water. Sorry, so yeah, so we do the next 24 hours and the next 7 days. We use the the Lake GBM regression model, and we use features. The features we use include the PM, that is particulate matter, timestamp, and cyclic features, lag features, and rolling features from timestamp as inputs for our model. And we managed to achieve a root mean square error of 12.85. I'm going to show you why this is important in the next slide. And this is an example of the output or the interface for the forecast model. So this was Thursday, which was yesterday, and you're able to predict air quality till Wednesday, which is basically 1 week, and it says it will be 37. And this is useful, especially for at an individual level, if you are trying to make, say, plans for maybe plan your week or plan your travel, and the tool is deployed on the mobile app. So it's useful for the general public, to make their decisions. And we also tested out air quality forecasting using satellite data. As I mentioned, our monitors only measure PM, that is PM 2.5 and PM 10. But there are also other pollutants that we are interested in, but do not have resources at the moment to monitor on the ground. So we explored using satellite data to forecast. Since we do not have ground monitors, we cannot necessarily predict at that time. So the initial use case we thought about was air quality forecasting. And to do that, we collaborated with Zindi, and it was in form of a challenge on the Zindi platform. I hope some people here are familiar with Zindi. The training set was from 2019 to 2020 August, and then the test set was 2020 August to December. And we included various gaseous pollutants to be forecast, and that included carbon monoxide, nitrogen dioxide, sulfur dioxide, and ozone. And we found that this was supposed to be root mean square error, is very similar to the value that we got with when we were building our forecast model using the low-cost monitors, meaning that it's actually very promising, because if we can get very good accuracy using the satellite data to be able to forecast air quality on the ground, then it's definitely potential we could sort of develop this tool further and actually be able to also analyze other pollutants that we are not able to measure with our low-cost monitors. The next application I'll talk about today is the calibration. So, like again, I mentioned we use low-cost air quality monitors, and one of the main concerns around using the low-cost air quality monitors is data accuracy. And for our monitors, we realize that much as they do have the similar trends with the reference grade monitor, you can see that they tend to overestimate air pollution values. So the blue is the reference grade monitor, which is the beta attenuation monitor, and the red line is the low-cost monitor, the air core monitor. And you can see that there is definitely overestimation of air pollution of PM. So what calibration does, it corrects this difference and definitely improves the accuracy of data from the low-cost monitor, since it's basically what we are relying on to monitor air quality in the region. So to build our calibration model, we use data from 2 collocation sites in Kampala, and we collocated 2 beta attenuation monitors with the air core monitors, and we used, of course, we did try out several machine learning methods, but the random forest and lasso regression modules were superior for PM 2.5 and PM 10 calibration. we were able to achieve very good accuracy. And our benchmark was basically the results we got from collocating the two reference grade monitors. We were able to achieve correlations of up to 0.97 after calibration. And as you can see from the graph, if you compare this from the previous graph, you can see that the difference between the values of the reference grade monitor and the low-cost monitors is now really small compared to before. We did what we also call the cross-site and cross-unit validation, because we are monitoring in several locations outside Uganda. So we needed to make sure that this model can also be applied in other locations that have different temperature and humidity, or basically different climatic conditions. As we know that, of course, temperature and humidity are one of the things that basically affects the readings from the low-cost sensors. So we tested out the model in another site in Uganda, in Addis Ababa, in Ethiopia, and Nairobi, and we are also working on testing out the model in different locations around the continent of Africa. We also tested out the model on Purple Air devices, because we are also exploring including devices for partners that may not necessarily be Airco devices on our platform. So we need to make sure the tool works for all this for the several locations and other devices as well. And so the calibration tool is basically calibration. When you are using low-cost sensors, it's like a key thing that you have to put into consideration, or like something that you must do. However, there are several people that are monitoring on the continent that do not have access to a reference grade monitor. And since you do need the reference grade monitor to develop your calibration models and actually test them, then that means they cannot actually build their own calibration models. So what we have done is we developed a user interface, or a tool, whereby other external users can access our calibration models. So what the tool does, it allows you to upload your CSV file with your local sensor data, and specify the required fields that were used to sort of train the model. And then in the background, of course, your data will be calibrated using our model, and you can download calibrated data. This is mostly useful for people who are monitoring on a small scale. Say you have 1 or 2 sensors, you can just upload a CSV of your data. And if you do have access to a reference grade monitor, but maybe you do not have the resource, technical expertise to develop the calibration models, you can also you can upload your collocation data. You just specify that you have reference grade data, so reference grade monitor data, and you are able to—
1 minute left, Priscilla.
Oh, sorry. Thank you. So yeah, you upload your data and you're able to train the model using your data, and then download calibrated data. I'm almost coming to, this is the last one. So the last application is the fault detection. Our network has grown. We have several monitors in several locations on the continent. So we need to be able to monitor the health of these sensors remotely, because we cannot go there all the time. So we also have a tool to remotely that is AI powered, that can allow us to be able to detect if a sensor is failing, it's about to fail. So we can send our team to go and check it out. And then it also saves time and money, because you don't have to fly out, maybe say to a different country just to check and see that, to know whether or not the sensor needs maintenance. Yeah. So basically, I hope you are able to get some ideas of how you can use AI in your work. It is a valuable tool, not just for collecting, not just for prediction, or like to say, I need more air quality data, so I've predicted and I have extra data, but it can also help you to get valuable insights that can support decision making. Thank you. And I would like to acknowledge contributions of the ECHO team and our sponsors.
Thank you, Priscilla, for a great talk. Once again, if you have any questions, please put them in the Q&A. We have time for a couple before we have to end this session. The first question is from Kobena, who's saying this is a very great study that you've done. Did you incorporate satellite information into choosing your sites?
Oh, that is for the sensor placement optimization? No, because when we are selecting sites, we are basically selecting sites for the low-cost monitors, and we are trying to see, we are looking at the, not necessarily the air quality in the location, because if you're to incorporate satellite data, then maybe, I hope I get your question anyway, but we are looking at sort of trying to understand grouping the profiles of the locations per se. So like if we assume that if the two locations have similar profiles, then the air quality is going to be similar. Yeah. So the short answer is no, we do not use satellite information.
Okay. There's another question from Enoch Dixon. Thank you for that great presentation. So do you employ any bias correction factors on the data to ensure the data quality of the measurements?
I assume you're talking about the calibration works, and that is ideally the whole point of the calibration works. So we do calibrate the data to correct the bias.
I think that's good enough answer. Any more questions? One right now from Varun Kumar. What challenges does humidity pose in outdoor operation of your PM measuring sensors?
Okay, so for our PM sensors, we use the light scattering technology. And what happens is when humidity is high, at least that's what studies have shown, when humidity is high, the particles tend to absorb the moisture. So it affects the size of the particle and in turn affects the categorization of the particle by the sensor. So it may be miscategorized as let me say if it's a PM 2.5 and it absorbs moisture, that's the best of my knowledge, it would then probably be miscategorized as a PM10 particle, and then your readings for the PM 2.5 may be lower and vice versa. So that is like the general effect that has been studied. There is a technical term, but it has sort of skipped my mind. So when we, and also this is like working hand in hand with temperature. So temperature also has the opposite effect. So it tends to say dry out the particle. So yeah, and that is why sometimes the sensors may either overestimate or underestimate the air quality, the pollution levels, basically. Yeah.
Thank you. Currently no more questions. Oh, there's one from Emily. Are there plans to extend this work to other measurements such as main gases, CO?
Which works exactly?
Sorry, I was typing fast. I was just wondering, because I think the study focused on PM, but you also get low-cost sensors that can measure like the key trace gases such as CO and ozone, and whether there are plans to extend this work.
Yes, so at the moment we are concentrating on PM, on on the ground, we are concentrating on PM and trying to cover as much area as possible within sub-Saharan Africa. With the gaseous pollutants, we are exploring using satellite data, and mostly because the reference grade monitors, as I mentioned, are very costly, and we cannot afford to have that in many locations. And then also calibration of gaseous, if you're to use the low-cost monitors for gaseous pollutants, then they are very tricky to calibrate. But when you're using low-cost sensors, you have to calibrate. So it becomes a bit tricky. So that is why we are exploring the use of satellite data for the gaseous pollutants. But on the ground, we are going to concentrate on PM.
Perfect.
Yeah.
I think that is going to be the end of this session. If there's just one more question, so we'll take that one. How can we get the data for West Africa, or the data just for southern part of Africa?
Okay, so all the data is accessible through our air quality data platform. And this is the link. It's platform.airco.net. You may have to set up an account, but it's free of charge. Basically, you just request for a username and password, and you'll be able to access any of the air quality data that we have on the network.
Great. I think now we're going to close the Q&A. And thank you again to all three of our speakers. It's very nice presentations. Emily, Max, you've got...
So yeah, that brings us to the end of our highlight talks for this time zone. So thank you again to all of our great speakers. The standard of presentations has been so high during this conference. We're really impressed. So now we'll have a short break for about 10 minutes. And this is where we say goodbye to our mid-career and senior scientists. But we hope to see you all later at the poster session. And for all the early career researchers, we hope to see you in 10 minutes in the side meeting room to start the icebreaker and our other interactive sessions. All right, thank you very much.